We're working on your course project proposals because I've been getting emails. That's great. I look forward to seeing these. I think there's some interesting ideas that I've seen coming around. Today I want to talk about time series modeling, and it's such a big subject that there are entire courses on time series modeling. We're not going to have an entire course on that here. But the good news is a lot of the work that we've already done to talk about Bayes nets and probabilistic models is going to make it easy for us to much more quickly go through several of the key topics in time series modeling. So actually, I just wanted to point out that I always put little reading suggestions here. In this particular case, chapter 13 of Bishop's book is actually very good and very thorough in terms of covering the material that we're going to cover today. In fact, much more thorough than we're going to be. And
just keep going.
Okay, all right, much more thorough than we're going to be. And so I'm going to skip over a bunch of intricate details of some of the manipulations of Bayes net inference, but those details are all available in Bishop's book. And certainly if you decide to do some work in this area, you should have a serious look at that. Are we okay here? Okay, great. So here's the simple question. You know, we've been talking about all kinds of classification and modeling problems. We've ignored the fact that a lot of data out there that we'd be interested in is really sequential data. So not a set of things, but a sequence of things. Sequence of stock prices, sequence of medical states that we've been in during our lifetime, sequence of, well, just about anything. Sequence of grades in our career and so forth. And so it's interesting to ask, what kind of maybe specialized to sequences learning algorithms should we think of? And so given the approach that we've been taking in the course, the natural way to pose the question is to say, well, what kind of probabilistic models of sequences should we think about? And so in one concrete way to ask that is to say, if we have a sequence of observations, O1, O2, up through O capital T, then what kind of joint distribution over those variables might we think about? And so one common approach is called Markov models. And the idea there is to simplify the description of the joint distribution over all the observations in the series by saying, well, observation at time t only depends on some limited history of the past. It doesn't depend on the infinite past. That's called a Markov assumption. And so put in our terminology of Bayes nets, we'd say, well, we have to represent the joint distribution over the sequence, and without loss of generality, without making any assumptions, we know we can represent that as some kind of a Bayes net, which just means that we're going to represent the joint distribution over all these observations at different times as the product, our usual Bayes net product. For each of those observations, the probability of it given its immediate parents in the Bayes net. And now the question is, what's the structure of the Bayes net? So the Markov assumption is simply this. It simply says, we could assume that the observation at time t depends only the immediate parents of the observation at time t is only the observation at t minus 1. And so then that would give us a Bayes net that looks like what? Well, actually one that looks just like this picture I have at the top of the page. So that would give us this kind of Bayes net, right? That is the Markov assumption. The Markov assumption is that we can represent the joint distribution on O1 through OT using this chain Bayes-Net structure. That's it. That's the Markov assumption. And then if we bring in what we know about D-separation, conditional independence, then you could tell me things like, oh, what that means is that, for example, if I think about the observation O3, well, that means O3 is, well, let's see, it's conditionally independent of its non-descendants given its immediate parent. So that means it's conditionally independent of O1 given O2. And by D-separation, it's also conditionally independent of O5 given O4. So that's nice. That means that this joint distribution is going to factor into some pretty small, product of some pretty small terms. And that's going to have all kinds of tractability advantages. And it's actually not a bad, well, I don't know. Might be a bad assumption, might be a good assumption. But if you think about something like, oh, let's say the stock market or the medical state that I'm in today compared to yesterday. If you think about it, let's think about my medical state today. It's not unreasonable to say that if O was not just a single value like my temperature, but a vector of values, like my temperature, white blood cell count, all these kind of medical signs, then it's kind of reasonable to say that the distribution on my values today, if I know all those values from yesterday, then given those values yesterday, it's conditionally independent of what they were the day before. That's a reasonable assumption if the vector of values that I'm observing about myself is fairly complete. Right? Now, if it's not very complete, then this assumption becomes obviously much more questionable. Right? Because then, well, if I'm not measuring my white blood cell count, but maybe indirectly my temperature reflects that, because if I have an infection, my temperature will be high, my white blood. So there might be kind of dependencies among those different variables, since if we don't include in my vector white blood cell count, then it might be the case that it would be useful to know the values from a couple days ago. Because if I've had a temperature for several days, probably my white blood cell count is higher, meaning that today's temperature would also be higher. So you see there's this kind of trade-off between how complete I make O sub I, or O sub t, the vector of observations, and how reasonable it is to assume that those are conditionally independent of my history given my immediate history. Does that make sense? Yeah? Is there any way to quantify that? I don't have one offhand, but it seems like one certainly could, right? You could certainly imagine measuring things like the mutual information of the variable observed at t-2 with respect to something like the conditional distribution of what you expect today given yesterday. So you could imagine ways of measuring that dependency. Might be interesting. Okay, so that's the idea of a Markov model. You hear about Markov models a lot. There's also something called an nth order Markov model, which is a simple generalization of this. It says that the immediate parents of the observation at time t include t-1 all the way up through t-n. Or put another way, the history more than n steps into the past. OT is conditionally independent of O sub t-n plus 1, given all these things. Okay. So what kind of a Bayes-Net does that give us? So that just gives us one that looks like so as before, OT depends on OT minus 1, but it also depends on OT minus 2. right? And O sub t minus 3, etc. So it gives us a much messier kind of Bayes net, but you get the idea. Okay, and this is called an nth order Markov model. And the bigger you make n, obviously the larger the terms in that product that the Bayes net is going to give us, and so the more complex the computations are that we have to do if we want to reason about that kind of distribution. Okay? Okay, so that's Markov models. Now, another term you'll hear, and I wanted to make you aware of the term. So when we talk about these models, just like with any Bayes net, if we really want to be specific, then we have to say, what kind of random variable is O? Is it a real valued variable? Is it an integer valued variable? Is it a vector of several values? And it can be any of those. There are all kinds of special cases of these time series probabilistic models. One that you'll hear about often in the literature is called autoregressive linear models. And for example, that just covers the case where our observations are real valued, so it's some real number, and we want to predict that real number. Maybe that's today's stock price for IBM. If we want to predict that from the past, then if we assume OT is a real number, and then it follows a distribution which is a normal distribution with some variance, and whose mean is some linear function of the last n steps. So this is an nth order autoregressive linear Markov model. Then that's what it means. You'll sometimes hear people talk about autoregressive. That means that you're predicting the value at t from earlier values of the same variable, autoregressive, at earlier times. And when you hear them say an nth order autoregressive model, it just means up to n time steps in the past, implicitly making the nth order Markov assumption. And if it's called regressive, as in regression, then that means O is real valued. And so a standard way of solving this is to just do linear regression, train a linear regression system to predict the value at t from these inputs. And if you go back and think about how we justified the maximum likelihood estimate for the parameters in logistic regression, in linear or logistic regression, in linear regression, we assume this model where there's some deterministic function of the inputs, and then into that we have added zero mean, normal Gaussian distributed noise. So this assumption just corresponds exactly to the assumption that we made when we talked about linear regression, minimizing the sum of squared errors being the same as getting maximum likelihood estimates of the parameters. And so that's what I mean when I say it's kind of fun that we're now at the point in the course where the stuff we've already learned, we can just import, talk about these entire, this is like a big research field. You can find conferences on time series modeling prediction that dwell largely on autoregressive. Lots of papers on this subject. But now you can see, to connect it into the ideas in this course, when you hear people talk about that, they're talking about a Bayes net with this nth order Markov assumption, and assuming O is a real valued variable. And if you want to justify linear regression as a way to solve this, you could say I could justify it by making the same assumptions we made when we justified in linear regression that maximum likelihood estimates correspond to minimizing sum of squared errors.
Do we call it just an autoregressive model or a linear autoregressive model?
Yeah. So the terminology is not perfect. To be careful, I should have said linear autoregressive model. If you look in Bishop's book, he says it must be linear to be called an autoregressive model, but I'm not sure how standard that terminology really is. So to be safe, you should add all your adjectives, and I should have here. Okay? All right, so that's Markov models. It's really a pretty simple idea. You can think of it in our language as making some commitments about what are the conditional independencies in the time series. Or it might not even be a time series. It could be any kind of a series. It could be a DNA sequence. And we just have a sequence of values. It's not a sequence in time. It's a sequence in space. And in fact, people do use Markov models, in fact, hidden Markov models, which we're going to talk about now, to model gene sequences in addition to modeling time series. Okay, so let's look at a slightly more interesting problem. I don't know how many of you have been to Las Vegas. I have to tell, I don't know how this, I have to watch what I say. I'm not the biggest fan of Las Vegas, but my brother-in-law called me up and he said, we're going to Las Vegas in June. And we are. So he's a very forceful person. And so I'm preparing for this. Anyway, this example is kind of drawn from this tension that I feel in my... So here's a kind of game that one might experience in Las Vegas. You get to bet $1, and then you roll a die, which the casino has given you, so you know it's fair. And then the person who works at the casino looks very trustworthy, doesn't he? He gets to roll a die too, but being somewhat of a shady character, he actually secretly has 2 die. One of them is a fair die, one of them is not. And he's very good with this, like, sleight of hand while you're sipping your drink. And so he can switch back and forth from the fair die to the unfair die. Anyway, you roll your die, he rolls his die. Whoever gets the largest number gets $2. If it's a tie, you just roll again. Okay, and here's the sequence of his die rolls, which to me looks like an abnormal number of 6s. And so I'm interested in estimating whether he's using 2 die, and if so, when? When is he switching back and forth between the two? He's a sophisticated shady character, so he doesn't just play the unfair die all the time, because I'm going to figure that out. But maybe he's toggling back and forth every once in a while. Okay, so there's a problem to think about. Real life problem. And so we'd like to come up with a learning algorithm that can look at that time series of simple integer valued observations and tell us with what probability is this guy using the correct die when, and with what probability using the incorrect one when. Okay, so now how are we going to do that? So as before, we have some bunch of random variables. I'll call them O1, O2, O3, up to O. I'll use capital T to indicate the last member of the time series. So again, I have these observations. And but now there's something hidden. It's not like the Markov model we talked about, where everything was observable. Now there's this other thing. Which die is this guy using? So I want to introduce in my probabilistic model an unobserved latent variable that influences what the observed roles are that I'm observing from this character. So let me call that variable the state. And I'll say, well, S could be, let's say, fair or loaded. So you could be using the fair or the loaded die. And now what I could say is, well, depending on whether he's using the fair or the loaded die, that's going to influence what the observation at time 1 is. And furthermore, the one at time 2 will also be influenced by whether he's using, etc. Okay. But now I also want to get in the idea into this model that there's some dependence of S2 on S1. Like the guy's going to try to not switch die on every roll because he's wants to make sure I don't observe him. So he's going to try to do that only once in a while. So what that means is if he's using, let's say, the fair die at time 1, then that influences the probability that it's going to be the fair die at time 2. And so forth. So it seems to me this is a more reasonable probabilistic model of that time series. So what this model says is if I want to know the probability of the numbers 1 through 6, okay, so let's be precise here. So O sub I, or t, I'll just say little t, is drawn from 1, 2, 3, 4, 5, 6. Those are the possible observations on the die roll. And clearly, and S could have the value 0 or 1, fair or loaded. It's just a Boolean variable. And I want to say, you know, conditioned on what S is, fair or loaded, we'll get some probability distribution over the possible rolls of the die. So it's pretty straightforward. Okay, and now I also have to say, well, there's some, if this is a Bayes nav, which of course it is, then it gives me the joint once I fill in all the conditional probability distributions that are required by this Bayes net, it gives me the joint distribution on the sequences of observed O's plus the sequence of unobserved S's. And once I have that joint distribution, of course, I can answer all the questions I could ever think of asking about marginals and conditionals and so forth on that joint distribution. Okay, so this is the idea of a hidden Markov model, because in this case we assume we have some observed things plus some hidden things. And just like as in any Bayes net, if somebody tells us what all the conditional probability distributions are, then we've got this inference problem, or a variety of inference problems we can solve, like what's the probability of him using an unfair die at time 3 given the observed sequence of O's. That would be an inference problem. And if they don't give us the conditional probability tables, but instead just give us a bunch of training data, like the ones we saw on the previous slide, that sequence of observed rolls, then we can ask, how can we train this Bayes net? Okay, so as with any Bayes net, with hidden Markov models, we have an inference problem, a collection of inference problems we could consider, and we have the learning problem. And the learning problem could be, as before, either in the case of fully observed data, where somebody tells us what's the value of these hidden variables S as well as the observed O's, and we learn from that, or it could be in the less kind situation of partially observed data, in which case we would use EM, right. Okay, so again, everything that we've talked about just comes exactly out in the wash here. Okay, so let's go forward a little bit more. I'm going to skip this. So in general, there are several interesting problems that are kind of whose answers have been well developed regarding HMMs. One of them is the inference problem of how likely is the sequence of observed O sub 1 through O sub t given an HMM, okay, which means given the structure and the conditional probability distribution. So we might call that the evaluation of the probability of an observed sequence. We can also ask questions about the unobserved sequence S. What portion of the sequence was generated by the fair die versus the loaded die? And that's really a question about the probability distribution on the unobserved S1 through ST. We might call that the decoding question. And then there's the learning problem. How loaded is the loaded die? What are the probabilities of 1, 2, 3, 4, 5, or 6 on that loaded die? And what is the transition probability of the sleazy casino guy shifting from the fair die to the loaded die? Or when does it end? The probability shifts back to the fair die and so forth. Okay, so that's really the learning of these conditional probability tables. So I like this example because everybody can relate to it. But there are a bunch of other examples that are very widely, where HMMs are very widely used. One of them is speech recognition. So actually the history of speech recognition is very interesting. Up until sort of 1989 or so, people tried all kinds of handwritten speech recognition algorithms. And around the late 80s, some people got the idea that they could use hidden Markov models to train a speech recognizer. And so in this case, the observed sequences are sequences, it's actually a real-time sequence of microphone signals. But if you want to make that discrete time, as we do with HMMs, then you can bin that into, if you can segment it into, say, phonemes, the different primitive sounds in speech, then you can get a time series of phonemes as your observed values. My friends in the speech community tell me there are about 39 phonemes in English. So that means we have a random variable with 39 possible phoneme values. We have a sequence of those. And now the hidden, what are the hidden states? Well, those could be the phoneme sequences or the word sequences or the syllable sequences or the, depending, you could probably frame this a number of different ways. And people have and have tried that. But you see how that maps directly onto this. It's isomorphic to the problem of finding out whether this, estimating whether that hidden variable is fair or loaded die. Here you're estimating from the observed phoneme sequence the probability that different word sequences are going on. Okay. So here's another, oops. So let me be a little bit more precise about what I mean when I say HMM. So to be very precise, it is, we could say it's just a Bayes net of that form, but to be a little bit more precise, an HMM is, to define one, we need to define these 5 things. We need to define what is the value of the hidden variable. That is, and we assume that it's a discrete valued hidden variable. So basically, we just have to say how many states can it have. In the case of the loaded die, 2 possible states. In the case of words in English, 60,000 possible values, but discrete nevertheless. We have to say what is the random variable O, what kind of values can it take on? Could take on these microphone signals or some summary of them in terms of frequency components. Could take just the, in the case of the roll of the die, could be just the observed die rolls, 1 through 6. We have to say the rest of these are really just a way of saying the CPTs, the conditional probability distributions, have to be filled in. So what are they here? Well, you know, because you know about Bayes nets, X1 has no immediate parents. And so we'll have to say for it, what are just the priors on each of its possible values, since it has no immediate parents. For each of these other things, we have to say what are the probability distribution over their values conditioned on their immediate parents. And that breaks into two kinds of things. The state transition distribution for any of these x's that we look at, well, their immediate parent is just the x before them, so we need to know that. That is, what's the probability of transitioning from phoneme u to phoneme k, for example. That was like a weak attempt to do a phoneme. And we also need to know what people call sometimes the emission distribution. For each of these O's, you can see its only immediate parent is its corresponding X. So you need to know those. Okay, but that's just a kind of long-winded way of saying it's a Bayes net. And of course, we need the conditional probability distributions on the Bayes net nodes. And of course, we also need to know for each of the variables in the Bayes net, what type of values can it take on? And what type of distribution are we going to commit to for that? Okay, so if, for example, if we say O can take on real values, then we have to say, well, what's the form of the distribution over O? Is it going to be a Gaussian distribution, a Poisson distribution, something else, and so forth? Here we what?
Making the assumption that this Bayes net is timing norm, so this CPD is associated with all the x's are the same and with all the o's are the same.
Very good point. Very good point. So the comment was, there's another assumption here that we don't necessarily make every time we write down a Bayes net, and that is that the parameters in some of these different conditional distributions are shared. And in particular, see the way I wrote this that there's this transition probability that covers the probability of transitioning from state I at time t to state k at time t plus 1. And implicitly I was saying, and I should have been explicit probably, that for all of these transitions, it's the same. So these all share the parameters. So we're assuming that, the probability of transitioning from a E to a U sound is the same no matter where it is in the sequence. So that's an additional assumption. And similarly, we're assuming that at any time, that this emission distribution is also time independent. So that if we're in hidden state Faraday at time 100, we'll get the same probability distribution on different rolls as if we're in Faraday at time 200. So again, we're sharing the distributions, the parameters in those tables. Without making that assumption, it gets to be really, really hard to train these things, as you can imagine, because if they could be different at every time, it's hard to get repeated trials that come from the same time that would allow us to estimate the parameters. Okay. All right. So in addition to thinking about this as a Bayes net, you'll often see for hidden Markov models in particular, this more state automata view of the system, which just talks about the probability of transitioning from state I to state j. And you'll often see these kind of diagrams, and sometimes you'll see those kind of diagrams. When I first started reading about HMMs, I was confused sometimes because I didn't realize there were two very different node arrow diagrams. They had completely different meanings that I was looking at. And so it's useful to just realize that these are two ways of characterizing them. This one is actually just characterizing the distribution. That. Okay, so more precisely, that is what we mean by hidden Markov model. So I want to talk about one more example, because I think this actually illustrates a kind of intriguing point. I could call this example, I'm a little surprised, the handwriting recognition problem. So just like we could train an HMM for speech recognition, we could do it for handwriting word recognition as well. But to start at the beginning, if I were to give you as homework a bunch of data which are pictures of handwritten characters, and I labeled some of them as C's and O's and E's and I's and different letters, and ask you to train a classifier, you could do that, I'm sure. And what you'd probably do is you'd say, well, I'm going to treat each pixel in the image as one of feature, right? You'd chop this image up into different features. And the value of the feature could be the average intensity inside there. So you might, for example, make a 30 by 30 grid and say, okay, I have 930 times 30 features. That's going to be my X1 through X900. And now I'll apply my favorite classifier to that, which might be logistic regression, might be naive Bayes, whatever. Let's say, for the sake of argument, that it's naive Bayes, because that makes my picture nice. So I'm going to say, here's some observation, and you're trying to train a naive Bayes classifier to tell me what character it is. Then your naive Bayes classifier, of course, is going to be a Bayes net that looks like this, right? Where S is now, which character is it? Right? So S comes from A, B, C, right? Okay, so you could easily do that if we had that homework assignment. What does this have to do with HMMs? Well, interestingly, if you wanted to have a more successful handwritten character recognizer, and the characters actually were in sequences of handwritten words instead of characters, then you would say to yourself, well, gee, there's some information in the identity of the previous character that helps me guess what the next character would be. There's not a uniform distribution. Given that I just saw an O, there's not a uniform distribution over A through Z. In fact, conditioned on O, the distribution is very different than even it would be if it was conditioned on K being the previous character. So you would probably say to yourself, there must be some way I can design some kind of joint classifier, some kind of collective classifier that would maybe, let's call this S2. If these were two characters in a row that I'm trying to decode, then you get the idea. You might say, well, I could decode these characters independently, but actually there is a dependency between them. And you'd end up making yourself an HMM as a way of coupling the predictions of your classifier about what are the different S's, the unobserved hidden character that was being written. And this would be an ideal way of coupling those. Well, if you assume that it's a first-order Markov, that character sequences are well modeled by a first-order Markov model. And if you thought it should be a second-order Markov model, you know what to do about it, right? You just put some more arrows between the different time series. Okay? So this is kind of cool because I like this example because what it underscores is another way to think about how we can use hidden Markov models is we can train sequences of classifiers whose classifier predictions are all coupled by some dependencies among those labels that we're trying to predict. It's just different English words for the same Bayes-Net idea, right? It's the same equations, it's the same idea. But it just lets you think about this as there's a whole set of applications where we might want to do this sort of thing. Right? Where classifying one example, where the class label for one example should somehow probabilistically couple to the label of some other example. Maybe if they're in a sequence, we do this with an HMM. They may not even be a sequence in general, but you get the idea. Okay? Okay, good. So, I see. This is a very sad problem I have here with my, wow, some kind of font problem. But so here's what that hidden Markov model would look like in this case, right? So just as before, I have some observed sequence of O1 through O5. These are different handwritten characters that I have to recognize. I have a hidden sequence of actual character labels. They're not observed by me. And if somebody gave me a pre-trained model, then I could use it to estimate the sequence x1 through x5. And if they didn't, but they gave me training data, then I could use EM to train this Bayes-Net, and I'd be good. And I think we already have kind of reviewed enough about the semantics, but you see what's involved here is you could think of, well, let's say it quickly and go through it again. So to define this hidden Markov model, what I have to say is, how am I going to encode the random variables O sub t? And as we just said, we might make that some kind of grid so that we can make it a vector of O1 sub 1 up through O1 sub 30 times 30. So O could be a vector of those intensities of the pixels. If it was, and they were real valued intensities, then what would you use for, what would you recommend that I use for the emission distribution? What kind of distribution would you use there if O is a vector of pixel intensities? Hint, what if I said, forget about the sequence, train a naive Bayes classifier? What would you do then? Say, well, I could use a Gaussian naive Bayes classifier, right? And I'd say, so if this is OT, let's call them OT1 through OT2 up through OT900, if that's my vector of pixel intensities in this 30 by 30 grid, then you'd say, well, if this is naive Bayes, then I would just say that each one of these could follow a normal distribution with some mean that's going to be conditioned on ST. S sub t, and some variance. Right? Just ask you to train a Gaussian naive Bayes classifier, that's what you do, right?
Since you've already divided it into a grid, is there an advantage to using the normal distribution instead of just giving a binary true-false label? Like if you divide it into rows, maybe a normal might be...
I see. So you're asking, is there a way we can do this binary? Well, if I assume the different pixels are real valued intensities, then I'll want to use some distribution that's good for real values, like a Gaussian. On the other hand, I could discretize those intensities so that they're all 0 or 1, black or white. And then I would use, then what would you recommend? Just a general Bernoulli distribution for each of those. But again, it'd have to be conditioned on what the character value S sub t is. And then, of course, in the Bayes, naive Bayes inference, when we go to solve for what's S sub t, we'd have to plug in the different parameters that go with those different assumed possible values of, oops, I switched from S to X. My apologies. Here I'm calling them X's. Okay? Okay, good. And so then, so this is really this little piece here. You could choose to implement that emission distribution by essentially treating that little piece as a naive Bayes classifier. Right? And then, in fact, it's the same naive Bayes classifier because it's sharing the parameters time independently across the entire sequence. Okay, now what about the other thing that we need? What would you recommend that we do for P of xt plus 1 equals state, let's say B, given that xt was O? Or actually, to make that not a 0, I'll use U. So what kind of distribution would you use for that? Yeah, just a simple discrete distribution. So I'll have a different theta for every possible, so I'll have a theta for B and U. In fact, I'll have 26 times 26 of these thetas. Modulo that some of them need to sum to 1, so I'm being a little sloppy here, right? But that's it. So it's just a standard Bayes net where, again, we have to pick how are we going to code each variable, and how are we going to encode what do we assume are the forms of the distributions. And now we've reduced the problem of representing the hidden Markov model to estimating the different parameters in our next state function and in our emission distribution. And oops, we left off one. We had to do the starting state. How do we say with the probability that state 1 will be the character, any given character? Well, we can just make up some discrete values for that too. That's it. Okay, so this is worth, I'm glad we went through this, because you can see now very clearly how this is literally, the way we've set it up, a sequence of naive Bayes classifiers. It's exactly what we've just defined, a sequence of naive Bayes classifiers whose labels, the X sub t's, are all coupled. And what are they coupled by? Well, they're coupled by these parameters that define the probability of the next character being B, given that the previous character was U, and so forth. And if somebody tells us those probabilities, we're sitting pretty. If they don't, we got to learn them. Okay, good. We kind of said this. Okay, so now this is a little bit review, but it's good to go through in this. So I want to go through some of those questions that we said we could ask about HMMs, some of the inference questions and some of the learning questions. So first question, how do we generate, if somebody gave us a well-defined HMM, like gave us all the parameters that we just defined, how do you generate a random sequence that follows the distribution, the joint distribution in this, implied by this Bayes net? Good. So we could just start at the beginning node, the node that has no parents, and take, randomly draw I'll draw a little x1 here from p of x1. That's one of the three things that we have here to work with, right? So we'll randomly draw that. We talked about randomly sample when we talked about Monte Carlo simulation of Bayes nets before. So for example, we could just pick a number between 0 and 1, and we could line up all the, uniformly pick a number between 0 and 1. We could create these little bins of the probability of an A, probability that S1 is B, probability that S1 is C, and so forth. They would, of course, sum to 1. When we pick our uniform draw from 0 to 1, we can just see which of those bins it falls into, and that'll give us the random sample of the A through Z according to their probabilities. Okay, then what? So we picked a little x1. Well, then given that, we just want to pick the descendant things. And fortunately, this Bayes net is a tree. Every node has just one parent, and so we can just chase down that tree very efficiently. Right? So now we'll randomly draw an O1, given the value that we chose for x1. And we'll also draw an x2, given the value that we chose for x1. So now we've got this guy, and this guy. And now we just continue. In fact, what I could say, is I could say t and t plus 1. And I could just say loop. There we are. Where uppercase T is the last thing in the number of time ticks in the sequence. Okay? So we just randomly draw a thing at the root of the tree, and then given what we drew, we know which conditional distribution to select out of the conditional distribution table, and there we go. Okay, so that was pretty easy. Here's a different one. How can we compute the sequence O1 through OT? So again, assuming that we know the HMM. So how would you do that? Well, it's not pretty, right? So it's a marginal, so we have to sum out over all the other marginals, right? So basically what we could say is we're going to sum over all the values at x1. We're only interested in the O's, so we have to sum out over all the possible values the x's could take on the joint distribution of that. So we could say, well, we know how to calculate the joint distribution, so I'll just write it down here. x1, x2, xt, O1, OT. You know how to solve for that because you just multiply together all the conditional probability tables. That's old hat. But now the problem is we have to sum out over the possibility that this equals I and J and K and all these in-between things. So I have 5 characters here. I guess I have to sum out over all 5. So I sum over I equals character A to character Z. And then J equals A to Z. You get the idea, right? So I have to do that for all the S's. And then if I sum over all of those, then this sum will, of course, be equal to the thing that I wanted. Right? It's just manipulating the joint. If you want a marginal, you just sum out over all the things in the joint that you don't care about and sum up their probabilities. Okay, now, the good news is that was simple to write down. The bad news is it's not a very satisfying approach in terms of complexity, especially if we have a long HMM. So the long time series is going to be really bad, right? Because now we've got a lot of things, an exponential number of, exponential in the length of our time series, a bunch of terms that we have to sum out over. So that's not so good. So anybody see a better way?
You can do it like quadratically by first, doing like, so the most standard thing would be like sum over x1 and then determine 1, and then from there you use x2 equal 2.
Right, right. Good. So you're suggesting a kind of dynamic programming approach that's similar to the variable elimination idea we talked about. And that's exactly the nice idea. And this is very well developed in the case of HMMs because it's such a popular BayesNet that people have really worked hard to get the most efficient ways of doing this inference. In fact, the nice thing about HMMs is that there's a whole collection of these kind of efficient inference algorithms that we can draw upon. They all share the characteristic that they're a kind of form of dynamic programming where you don't actually consider the way we did in this brute force solution. You don't say, well, I'm going to consider every single term in the joint distribution. Instead, you look at the dependencies and the conditional independencies that are available, and you define a more handcrafted to the HMM structure, specialized to the HMM structure approach. So let's see this particular one. Suppose we do want to compute this. Then what we can do is we can define this intermediate term, which I'll call alpha sub t of k, which I'll define this way. So alpha sub t of k is just the probability of the observations from starting at time 1 and stopping at time t. So all of the observations up to little t. And the value that x sub t equals k. Sounds like a weird term to calculate. But as we'll see, if we calculate it, we can do it efficiently and recursively, and then we can just easily get the answer that we're interested in. Okay, so what is alpha sub 1 of k? And just to make that clear, that's, according to this, that's the probability that the variable O1 takes on its little observed value O1, right? And since we're talking about 1, we're only interested in that one observation. And the probability that x sub 1 takes on the value k. Right, that's the definition. So how do I get that? Out of the terms that are available in the BayesNet? So it's actually very simple. It's just the probability that x1 has value k times the probability that O1 has its value, given that x equals k. That's alpha 1. Now, the interesting thing is, what is alpha 2? Let's write that up here. So alpha 2 of k. So what is that? And again, definitionally, that's just the probability that O1 takes on its observed value and O2 takes on its observed value. Now that we're at t equals 2, we care about both of those, and that x2 takes on the value k. So how can I compute this in terms of alpha 1? So if you looked at for a while, you notice that's just, let me do this. I'm going to sum over J the alpha 1s. How do I want to write this? I'll write it out. I'll write little o1 and x1 equals j. That's alpha sub 1j, right? That's alpha 1j. That's what we just defined down here. So if I sum that out over j times the probability of x2 being k, given that x1 was j, now I've got the probability of observed O1 and x2 equals k, because I've summed out over all the things x1 could be. And now I still need the probability of the observed O2, but because that's conditionally independent of everything else given xk, that's just the probability that O2 takes on its observed value given that x2 equals k. Okay. Okay, so what I've done is I've managed to write this alpha sub 2 of k recursively in terms of the alpha sub 1s of all the possible states j. And so there's a recursive thing. In fact, in general, alpha sub t plus 1 is just the sum over j equals 1 to n, the possible number of states that x could take on. 26 in our case of characters, of alpha t of j, just like we were doing up here, times the probability of xt plus 1 being k, whoops, equal to k, given xt was j, times the probability of the observed t plus 1 being its little value, its observed value, given that x t plus 1 is k. So there's the generic recursion. And so you see what you can do is to just run down the chain. I do this t times, so it's linear in t. Each time I'm relying on the alpha that I computed at t in order to get the alpha at t plus 1. So I've got this dynamic programming style computation that has n iterations, or sorry, t iterations, where t is the length of the time series, instead of looking at summing up these exponential in t things. Okay? So that's good. Oh yeah, but my problem was I wanted to compute this. So given all these alphas, how do I compute the probability of the observed sequence? Yes?
Alpha sub t, sum over all the k's of alpha sub cap t.
Exactly. So if we just go back and look at the definition of alpha sub t, it's just the probability of all the observations up to t and xt taking on a particular value. So this is, if I'm interested in the observations all the way through the end, uppercase t, that's just alpha uppercase t, the final alpha, for state k. But oops, I don't know what state k is, so I got to sum over all the possible k's. So again, I'm just marginalizing out the thing I didn't care about, which was xt, and leaving behind the probability of that entire observation sequence. Okay, so this is a very nice idea you see that it requires thinking clearly about this kind of recursion and coming up with a good idea of what term to center that recursion around. Like, the real insight here was figuring out that alpha, that particular definition of alpha, would be a good thing to be computing along the way. And fortunately for us, people have worked this out for HMMs, and so we can use this to do efficient inference of at least this kind of term for any HMM. Okay? So here's another one. We might be interested in make sure I get all my I's and T's crossed and dotted on this one. Here's a different one. So we could ask, well, it's another reasonable state. It's like, we want to know at time t, given the observed sequence, what's the probability that that shady guy was using the fair die versus the fake die? So what's the probability of the hidden variable x sub t being fair versus unfair, conditioned, given all the observed data that I have? That's a reasonable question to ask. And again, the key here is to define some term. In this case, we'll call it beta. Here's our old friend alpha that we just saw. We can define a different term. Beta has a different form from alpha. You know, in a funny way, it's like the complement of alpha. Alpha, again, was the probability of the joint distribution on all the observations up to time t plus x sub t having a particular value. We'll define beta to be the probability, beta sub t will be the probability of all future observations together with the probability, or conditioned on the probability, conditioned on xt being k. And here's where I say we're not going to go through all the details of every one of these recursive things, and Bishop's chapter does a very nice job of going through these. But if given enough time, you could also figure out a recursive way of calculating these betas that's linear in the length of the time series, just like we did for alpha. It's very similar in spirit. And then, given that, the nice thing is if we wanted this thing that we want to know, that kind of follows just from the alphas and the betas, right? Because, well, what is this one? So if we want to know this, then by definition of conditional probability, that's just the probability of all those things being true over the denominator, the conditioned things happening. How do I calculate the denominator? We just said that, right? That's just the sum over k of all my alphas, alpha t. And again, that's the uppercase t. That's the final alpha t. That's that one. And what's the numerator? Yes. Good. All right? Because this is just the product of that and that. So these are ways you can, so these alphas and betas give us nice linear complexity ways of manipulating the probabilities in these HMMs. And that's the key to doing this kind of recursive stuff. There are more. There's more than alpha beta. There are Greek characters I can barely pronounce, as well as gamma and delta. Another one that's very helpful is this one, delta, which is a recursive way of computing the maximum probability over all possible assignments of the latent variables, of the hidden variables, up to time t, plus a commitment for time t, together with all the observations up to time t. And if we use that one, then we can in an analogous way to how we saw alpha and beta, we can solve the key inference question: what's the most probable sequence of unobserved states, of hidden states, given the observed sequence? And again, it's based on a very similar kind of recursive computation. All right, so that's inference in Bayes nets. That's inference in HMMs as a special case. And this is really, I mean, HMMs are important enough that it would be worth going through this just for HMM purposes, but it's also really a typical case study of how life with Bayes nets goes, which is, it's a beautiful general purpose idea, but then sometimes the inference problems can be very intractable. And so you can end up sometimes having to spend a lot of work to figure out how are you going to tractably calculate answers to the inference problems that you care about. And the fortunate thing about HMMs is it's a tree-structured Bayes net, and so it admits some very nice, efficient, tractable, closed-form solutions for pretty much everything that you want to ask about in terms of marginals and conditionals. So if I ask about learning HMMs, I bet you already know the answer. If they're fully observed data, you have no trouble training a Bayes net with fully observed data. In fact, if we take that case of training HMM, which is a sequence of naive Bayes classifiers for the character recognition problem, and you had all observed data, it's pretty obvious how you do that, right? You just train your naive Bayes classifier using data for every character you could get your hands on in the sequence. And the transition probabilities, you just look at, you know, the counts of how many times you went from a B to a U, how many times you went from a B to an A, to a B, to a C, to a D. You get those proportions that would give you maximum likelihood estimates you're there. If it's not fully observed data, then you have the problem of using EM to do this. And that's possible too. And in fact, there are people put a lot of work into doing that as efficiently as possible. So there's an algorithm called Baum-Welsh, and sometimes called forward-backward. Algorithm that's used for the EM step, but again, it's not going to be a surprise that to train this, we would estimate the distribution in the E step. We estimate the distribution P of x1 up through xt given the observed things. And on the M step, we choose our parameters, all the parameters in the hidden Markov model, to maximize the expected full data likelihood log. Given theta. And if you look in Bishop's chapter, you can see the details of the dynamic programming things that you want to do in order to make that work. Essentially, it comes down to having to get the expected numbers, the expected values for things like how often do I transition from state A at time t to state B at time t plus 1. You have to get expectations on those transitions and also on the emission distributions of, what's the expected value of seeing this observed value conditioned on this unobserved S. So basically you end up having to get the expectations on those counts. Okay, so I'm glad we got to look at this. I want to just end by showing you very briefly a couple other styles of Bayesnet time series models. So HMMs are probably, if you're only going to know one, that's the one to know. But once you get this idea that you could just use any kind of Bayesnet if you're willing to put in the effort to derive the inference in learning algorithms, then it's interesting to ask what other types of Bayesnet structures have people come up with. So the one on top here, this, by the way, is from a very nice overview paper. I'll put a pointer to it on our website by Zubin Garamani. But that top one is an HMM where instead of having a single integer valued hidden state, we have a vector of hidden values. It's called a factorial HMM. And you could easily imagine, you know, if you're, for example, trying to predict the, I don't know, stock prices tomorrow, time series of stock prices, you might say, well, I need several hidden variables, one for the, you know, demand for IBM computers, one which isn't directly observable, one for the supply of IBM computers, one for the, maybe represents competitors and what they're going to do to the stock price. So you might think that there are several different hidden variables. And so a factorial HMM is a way of saying, yes, our observed values and our hidden. And we can write a time series model like that. This one down here takes it to the next step by saying, well, it can also be a tree-structured thing where this is kind of an elaboration of the one on top. So this one on top essentially says the chain of the sequence for each of those hidden variables are independent of each other, whereas this one says, oh, no, the values of this one depends on that one and so forth. So they can be coupled too. So I think that's all. Oh, there's one more. There's also the idea of switching state models. This one is kind of interesting. This one says, well, I can represent the hidden sequence using different variables, but essentially what this model says is y at any given time depends on just one of these. So y is his variable for the observed thing. So it depends on just one of these. And then S is a integer valued indicator that chooses which of S chooses which of the X's Y depends on. And so this is a way of kind of saying, you know, if you're doing the stock market, some people say sometimes it's a bear market, it's going down, sometimes it's a bull market, it's going up. And so this is a way of saying, well, I could have these two regimes. The top row of X's represent the bear market dynamics. The second row represent the bull market dynamics, and S chooses between those. And so then I can learn the bear and the bull market dynamics and separately learn how to choose between them as my way of modeling the full time series. So this is just a sampling of some of the ways you can set this up. And people have explored a lot more than these, but it gives you an idea of just how rich the space is. And maybe some of these will be relevant to some of your projects if you're looking at sequential data. And I'll put a pointer to Zubin's overview paper, which is where I took these diagrams. It's a very nice paper that unifies what we've talked about with Bayes nets with more traditional literature on time series models. Okay. All right, thanks.